Hey everybody, welcome back to Mr. A's Geometry course. Today we're going to be reviewing quadrilaterals in our Unit 7 study guide. Let's get into it. In our first example, we're going to be reviewing a basic property of a parallelogram, which is that opposite sides are congruent. We're told this is a parallelogram. Opposite sides need to be congruent, so that means this side xy needs to be congruent to wz. So 4a has to equal 3a plus 7. If we subtract 3a from both sides, we'll get a equals 7. Easy enough. These opposite sides also need to be congruent to each other. So that means the 2b has to equal b plus 11. If we subtract b from both sides, we'll get b equals 11. Nice easy start here. Opposite sides are congruent in parallelograms. I didn't mention this in any of my lessons for Unit 7, but there's actually a symbol for a parallelogram, which is a little block there in front of our STU. So we're told this is a parallelogram. We're going to find the indicated measure of angle RUT. So we're going to ignore the B that's here in the figure. We're just going to find the measure of angle RUT up here, which requires us to know where that angle is. If we were to highlight from R to U to T, we would highlight the sides of the angle. The angle itself would be everything in between those sides. So it's actually this whole corner down here at U that we're trying to find. A skill that may help you visually in an example like this is imagining the figure without the diagonals if we're trying to find the measure of the whole corner. We need that whole bottom left corner. And we're able to do that because we actually have the whole top left corner. You notice this top left corner where R is split into a 30 and a 25. Well, if we combine those, it gives us that whole measure. 30 plus 25 gives me 55 degrees up there in the top left. And the reason that's relevant is we can now identify these as consecutive angles. And in parallelograms, consecutive angles are supplementary to each other. So that x plus 55 has to add up to 180 degrees. If we subtract 55 from both sides, we're going to get 125 degrees, option B, for the measure of angle RUT in this example. Example 3 is asking us to prove that this figure is a parallelogram. It says determine if it's a parallelogram, justify our answer is just proving whether it is one or not one. It's giving an explanation for why. And this is a little different than just knowing the properties of a parallelogram. This is actually using the converse of properties. What we see here is that opposite angles are both 36 and opposite angles are both 144 degrees. That is a property of a parallelogram, opposite angles being congruent to each other. So by the opposite angles converse, if the opposite angles are congruent, then the figure must be a parallelogram. All right, and that is our first option here. Yes, this is a parallelogram because both pairs of opposite angles are congruent to each other. Still reviewing the properties of a parallelogram here in example 4. This time we're given some information kind of funky the way it's placed in here. These are all diagonal measures that are given to us. So that 3y minus 5 is this chunk right here, y plus 5 is this chunk, 2z plus 7 is this chunk, z plus 9 is this chunk. And the property to know here is that in a parallelogram, diagonals bisect each other. They cut each other in half. So if you were to imagine that JL was 10 units long, well then this piece would be half of that, it would be 5. And this piece would also be half of it, would be 5. The key is they are the same length. So these two measures here, the 3y minus 5 and the y plus 5, have to be equal to each other. 3y minus 5 has to equal y plus 5. Okay, if we can subtract the y from both sides to get the y's to our left, we get 2y minus 5 equals 5. We can add 5 to both sides to get that 2y alone. It gives me 2y equals 10. And we can divide both sides by 2, so y equals 5. So to make this a parallelogram, we need those congruent pieces, which means that y would have to be 5 units long. Now we're looking at z on our other diagonal. The same thing happens. If we imagine that that's 20 units long, well, this half would have to be 10, and this half would have to be 10. They would have to be equal to each other. So 2z plus 7 has to equal z plus 9. Again, we can do algebra here. We can subtract z from both sides. We would get z plus 7 equals 9. We can subtract both sides by 7 to get z equals 2 in this example. We have two questions here involving a rectangle. Directions say we're going to use this rectangle for questions 5 and 6. Our first question here, 5, is asking us about a pretty simple property, which is that the diagonals of rectangles are congruent to each other. Meaning if AC was 10 then BD would also be 10, which means that AG would be 5, and GC would be 5, and BG would be 5, and GD would be 5. The key here is to know that all of these pieces here would be congruent because it's a rectangle. We're told AG is 4W minus 7, so 4W minus 7 right there. DG is 2W plus 3, so 2W plus 3 right there. And even though they're on different diagonals, as we just discussed, these pieces have to be congruent to each other. So we can solve for W by setting 4W minus 7 equal to 2W plus 3. Let's do the algebra. Subtract 2W from both sides. We get 2W minus 7 equals 3. We can add 7 to both sides to get 2W equals 10. We can divide both sides by 2 to get W equals 5. Now I love this problem because even though that property is simple enough, diagonals are congruent, the actual answer to this question is really complex because it's not asking me just to find W. And notice that 5 is actually one of the multiple choice options, right? So we have to be careful. We have to plug this in. We need to find DB, the length of that whole diagonal, which we don't have an expression for right now. So if we are ever stuck and we're not sure, like I don't have something to plug into to give me that answer, we'll plug it into something that you do have and see if you can find out more information. Like I can plug it into DG right here. So I'm gonna do that. I'm gonna figure out how long that part is. DG, we know equals 2W plus 3, and I know my W is 5. So I'm gonna do 2 times 5 plus 3, which would give me 13. So I know now, and I'm just gonna put this up here visually for you, I know that this is 13. And I know that rectangles are parallelograms, the diagonals have to cut each other in half. So if this is 13, then that half there has to also be 13. Which means I can now find DB by just doing a little segment addition there. I can take the 13 from DG, add it to the 13 from GB, and it will give me the length of that whole diagonal, just 26 units long. Notice the 13 was even an option down here. So those problems are tricky. Let's make sure that we're plugging all the way in until we answer the question that's being asked. Example 6 is asking us to find an angle measure in the same rectangle. Now, the big picture key in this is knowing that rectangles have 4 right angles. So I know that in all 4 corners there needs to be a total of 90 degrees. The diagonals are going to split that 90, and it can split it in numerous ways. It doesn't have to be like cut in half, 45 and 45. It could be 60-30, 70-20, and so on. So we have to determine where these angles are given to us. Use logic from there to find the measure of the angle that's being asked. We're told angle BDC is 2B plus 15. So BDC, that's this little angle right here in the corner where D is 2B plus 5. I'm going to go ahead and put that in there, 2B plus 5. We're told that angle ABD is 3B plus 1. So ABD, well, that's this little angle up here, 3B plus 1. And before we continue on with anything, we need to recognize something that's a property of a parallelogram. In parallelograms, we have opposite sides that are parallel, meaning that when diagonals are present, we're going to have alternate interior angles. I'm going to try to highlight them here for you. Those sides would be parallel. This is a transversal. Where our B's are located are like right here and right here. Those are alternate interior angles. And on parallel lines, which rectangles have because they're parallelograms, alternate interior angles have to be congruent to each other. So we're starting this problem with identifying these are alternate interior angles, and I can solve for B by knowing that alternate interior angles are congruent or equal on parallel lines. So 3B plus 1 has to equal 2B plus 5. We can subtract 2B from both sides. Boom, that gives me B plus 1 equals 5. We can subtract 1 from both sides. That gives me B equals 4. If the question was find B, we'd be done, but it's not. We have to find the measure of angle ADB. Where is angle ADB? ADB, well, that's this little angle right next to the 2B plus 5. I'm going to put an X there. It's an unknown thing. Okay, so I don't have something to plug in though, right? Because this is X, not B. I know B is 4. I don't know what X is. I can't plug this in here. I don't have an expression. What do I do? Again, if you're not sure, just plug it into the stuff that you already have. Find out some more information. For example, I'm going to plug it in here to this 2B plus 5. So that is angle BDC. I'm going to be plugging that B equals 4 into here. Angle BD, that's a B. BDC is 2B plus 5, and I know my B is 4, so 2 times 4 plus 5. Well, 2 times 4 is 8. 8 plus 5 gives me 13 degrees. I'm gonna update my figure here. I know now this angle is 13 degrees. I hope you can see why that's relevant, why that's useful for us. If I know the whole corner is 90, I now have a very easy calculation to find this angle ADB that we need here. That angle plus 13 has to equal 90 degrees. So the measure of angle ADB, that's where my x is, plus 13 has to equal 90. We just need to subtract 13 from 90, and we can determine that the measure of angle ADB is 77 degrees. Again, that's for this example 6 on our study guide. Example 7 is reviewing a property of a rhombus. We're told a few things, that yk is 9, yz is 16, the measure of kyz is 47 degrees. We're being asked to find the measure of angle RYK. So these first two things here, yk and 9, yz, 16, is not actually relevant for the problem that we're solving here in this one. RYK, we got to find that angle. Where is RYK? RYK is right there. It's this little angle here. I'm going to go ahead and just put an X there. It's an unknown thing. I need to solve for that angle. We're told KYZ is 47 degrees. That must be useful. That's another angle measure. Let me find KYZ. KYZ. Okay, that's this angle right here. It's 47 degrees. So I'm going to go ahead and update that. Put a little 47 degrees there in that corner. And the property that matters here is that in a rhombus, which our directions say this is, the diagonals are bisecting these angles in the corner. So this whole corner where P is getting cut in half, that means those two angles have to be equal. This corner where R is cut in half, those two angles are equal. This corner where Z is getting cut in half, those two angles are equal. This corner where Y is getting cut in half, these two angles have to be equal to each other. So if this is 47, X is 47, angle RYK is 47 degrees. We have here a kite. The directions tell us a kite. The markings do too. We have consecutive sides with 1 dash, consecutive sides with 2 dashes. I know it's a little blurry here, but that's what it shows. Kites don't have opposite sides that are congruent. They have consecutive sides congruent, like these here. We have to find the measure of angle S. So the property that matters here is that a kite is going to have one pair of opposite angles that are congruent to each other. We just need to know where those angles are. And those are always the angles that are the included angles, so that means they're in between the non-congruent sides. So this side is not congruent to this side. The included angle of those two sides is this angle, angle S. This side is not congruent to this side. The included angle of those is angle Q. So these angles have to be congruent. That's one of the keys to unlocking here the measure of angle S. We got to find angle S. Let's say it's X, it's unknown. Well, again, we just discussed how these angles have to be congruent, so that means angle Q is also X. The key from here is knowing that the measure of the four angles in any quadrilateral, any four-sided shape is 360 degrees. If you ever forget that fact, hopefully you remember from 7.1 that we have this formula that we can do to find the measure for the sum of interior angles. That formula was n minus 2 times 180. We'll see that again later in our study guide, where n is the number of sides. So if I do 4 sides minus 2 times 180, that 4 minus 2 would give me 2, and 2 times 180 would give me 360 degrees. So I know all 4 of these have to add up to 360 degrees. And so we just have algebra from there. The 2 x's and the 36 and the 124 have to add up to 360 degrees. X plus x gives me 2 x's on the left. 36 plus 124 adds up to 160. That's just combining like terms. I can then move that 160 by subtracting it from both sides to get 2x equals 200. Then I can divide both sides by 2 there to get x equals 100 degrees. So measure of angle S, 100 degrees in this kite. In example 9, we have to classify the figure. That means we have to say whether it's a parallelogram, rectangle, rhombus, square, trapezoid, kite. We have to say which of those types of quadrilaterals this is. And we're doing this based off of symbols, not based off of what the shape itself looks like, but what the markings on the shape tell us about that figure. For example, all 4 sides have 1 dash on it. Well, what does that mean? That means that all 4 sides are congruent to each other, which is a property of a rhombus. So okay, we have a start here where I got the properties of a rhombus. All 4 sides are congruent to each other. However, we also have 4 right angles in our shape. Well, that's the property of something different. That's the property of a rectangle. Rhombuses don't have four right angles. Rectangles don't have four congruent sides. Therefore, this shape has to be the one that has the properties of all of our special parallelograms, which is a square. So yeah, it looks like the shape of a square, but the markings prove it for us. All four sides are congruent is from a rhombus, four right angles is from a rectangle. Only the square has the properties of both a rhombus and a rectangle. So that's a square. In example 10, we have to find the measure of angle T and angle Y. Right, they're not the same. Even we only have one of the correct answers actually in the multiple choice. So we're just going to ignore that multiple choice down there. Instead, what I'm going to do is I'm just going to put an X at angle T. I'm going to put a Y, or we have Y's there. I'm going to use different letters. I'm going to put an A at angle T. I'm going to put a B at angle Y. We're just going to solve for those variables here in this problem. The key is classifying our shape. What type of figure is this? Well, it's not a parallelogram because I only have one pair of opposite sides that are parallel. That is a trapezoid. And it's a special type of trapezoid. Remember, we call these parallel sides the bases. The other sides are called the legs. The legs happen to be congruent here in this. That makes this an isosceles trapezoid. And the important property of an isosceles trapezoid that matters here is that base angles are congruent. So this is a base up here, TV. That means angles V and T are base angles. They touch the same base. Base angles are congruent, so A must also be 60 degrees. A is 60 degrees. How do we solve for B? Well, we can do that without the use of the property of isosceles trapezoids, or at least at this stage, now that we know this is 60 degrees. So for any trapezoid, because there's a set of parallel sides, we're going to get consecutive interior angles. All right, hopefully you can see that. If I were to like extend this right here, extend this TY over here, those are consecutive interior angles A and B there. They're in between the parallel lines on the same side of the transversal. And on parallel lines, these guys are always supplementary to each other. They have to add up to 180. So I know that that B plus the 60 degrees that I know for angle A has to equal 180 degrees. If I subtract that 60 from both sides, we're going to get a measure of 120 degrees for B. Okay, before I go on to the next thing, it's important to note I negligently left out problems regarding the mid-segments of trapezoids. That's definitely something that you're going to be assessed on in any Unit 7 test for geometry. Please make sure you review mid-segments of trapezoids. That will be on your Unit 7 test. You can look at my previous video, 7.5 on trapezoids, to find that information. In example 11, we have a great question here. It says, which statement, which of these multiple choice things here proves that this figure is a parallelogram? Okay, so let's evaluate each of them. Option A says angle Q is congruent to angle S. Well, if we looked at that without the diagonals in, that would be this angle congruent to this angle. Well, that's opposite angles being congruent to each other, but we know in a parallelogram, both pairs of opposite angles have to be congruent. So because T is not congruent to R, that does not give me parallelogram. All right, let's look at our next option. Let me go down this way. We're going to go to C here. All right, just going to do a little process of elimination here for C. It says QT is parallel to RS. So this left side parallel to the right side. Again, if you look at that without the diagonals, well, that is kind of a property of parallelogram. We have opposite sides that are parallel, but we don't have proof that the top and bottom are parallel. And we need that to know it's a parallelogram. Both pairs of opposite sides have to be parallel for a parallelogram. So that doesn't work. Right, option D will also not work. Let's look at it really quick. It says angle Q plus angle S equals 180 degrees. Well, again, Q and S are these angles that are opposite from each other, this corner and this corner. Okay, in parallelograms, it's not the opposite angles that add up to 180. It's actually the consecutive angles that add up to 180, like those right there. So this does not give me any evidence of opposite angles being congruent to each other for this to be a parallelogram. Right, so that leaves us with option B. So process of elimination, we know this one has to be right. This is that unique way to prove that parallelograms or that quadrilaterals are parallelograms, because this isn't a converse of a property, right? This says that QR is congruent to TS. That would be this top side congruent to this bottom side. And it says the same pair of sides are also parallel to each other. So this side is parallel to this side. That is a way to prove and justify that a figure is a parallelogram. It's the last one we learned in 7.3. If one pair of opposite sides is both congruent and parallel to each other, then that figure has to be a parallelogram. So option B here will ensure that that's a quadrilateral, a parallelogram. In example 12, we are going over side measures for kites here. It says JKLM is a kite, right? We're told that JK is 10 units long, and we're told that JM is 35 units long. Before I look at the rest of this, you need to remember that in a kite, the congruent sides are not opposite of each other. They are consecutive sides. So what this means is there's another side that's going to be 10 units long, there's another side that's going to be 35 units long, but again, they're not across from each other. So LM here is opposite of the 10, but it's not going to be congruent in the kite. It'll be the consecutive side, which I have to be KL, because obviously this consecutive side is not 10. So it's got to be this side that would also be 10, therefore this side would also be 35. That's the key here in solving for the variables in this problem. Is that all we're doing? Yeah, we're just solving for x and y. So LM is 4x plus 15, so 4x plus 15 goes here. KL is 2y, so 2y goes there. And again, as we discussed, opposite sides are not congruent in the kite, it's the consecutive sides that are congruent. So these have to be equal here. 2y has to equal 10, nice easy, divided by 2 there to get that y is 5 units long in this example. And again, these sides must also be congruent. 4x plus 15 has to equal 35. 4x plus 15 equals 35. We can subtract that 15 from both sides. We get 4x equals 20. We can then divide both sides by 4 to get x equals 5 as well in this example. In example 13, we have 3 scenarios where we have to find a missing angle inside of a shape. Right, we told you about this earlier. We're going to have this problem where we have to do n minus 2 times 180 to find the measure or the sum of the interior angles of a shape. So we have a 5-sided shape. That means to know what all of these add up to, I have to do 5 minus 2 times 180. Again, the 5 comes from the number of sides or the number of angles or the number of vertices. Those are all the same. 5 minus 2 times 180. 5 minus 2 is 3. 3 times 180 gives me 540 degrees. That's not the answer to the question. That's what all of these have to add up to. They have to add up to 540. So what we can do from there is just algebra. X plus 85 plus 103 plus 121 plus 68. All those angles have to add up to 540 degrees. Let me get a calculator here really quick to combine all of these like terms. If we do 85 plus 103 plus 121 plus 68, those all combine to give me 377 degrees. I can then get x by itself by subtracting that 377 from both sides. So 540 minus 377 gives me 163 degrees for x on that polygon there. All right, and our next polygon, there is a different number of sides. Therefore, we're going to have a different sum for all of these angles. Let's count. We got 1, 2, 3, 4, 5, 6 sides. Those dashes aren't meant to show congruency. They're just to help me count. 6 sides here. All right, so that means we need to do 6 minus 2 times 180 to get the sum of these measures. 6 minus 2 is 4. 4 times 180 should be 720 degrees. So all of these angles have to add up to 720. So that means x plus 120 plus 72 plus 149 plus 121 plus 117 has to equal 720 degrees. Again, I'm going to combine all of these like terms here. So 120 plus 72 plus 149 plus 121 plus 117 gives me a total of 579 degrees, which I can now subtract from 720 to get the measure of our missing angle here. So 720 minus 579 gives me 141 degrees for x in that polygon. Our last example, or last scenario here in this says find the interior angle of a regular pentagon. Okay, first, a regular polygon is a shape where all the sides are congruent and all the angles are congruent to each other. So all the angles inside of this shape are the same amount of degrees. And our shape is called a pentagon, therefore it has 10 sides, 10 angles, 10 vertices. Right? So what that means is to find the sum of all the angles is we're going to do 10 minus 2 times 180. 10 minus 2 is 8. 8 times 180 gives me 1,440, I believe. Let me double check. 1,440. And again, because all of the angles are congruent, I meant to point an arrow here because that's what regular means. Then all we have to do is divide this by 10. That amount of degrees is evenly split to all 10 angles inside of our figure. So 1440 divided by 10 tells me each individual angle in this regular decagon, 10-sided shape, will be 144 degrees. In example 14, we're now looking at exterior angles of polygons. So again, in 13, all those angle measures were inside of the polygon. Now we're extending all of our sides to give us exterior angles. And the rule here is no matter how many sides, no matter how many exterior angles, the sum has to be 360 degrees. So whether it's 6 angles like it is in this figure, or 5 angles like it is in that figure, or 12 exterior angles like there would be in a 12-sided shape, they have to add up to 360 degrees, no matter what. So we'll keep that in mind as we solve for these variables. Just algebra here, y plus 61 plus 2y plus 35 plus 50 plus 59 has to equal 360 degrees because they're exterior angles. Combining like terms here, I have y and 2y, that gives me 3y's. And then when I do 61 plus 35 plus 50 plus 59, let's see what we get. 61 plus 35 plus 50 plus 59 gives me 205. Let's write that in black here. It gives me 205 after combining those. I can subtract that 205 from both sides. I'm going to get 3y equals 155. And then if I divide both sides by 3, I'm going to run out of room here. 155 divided by 3 is going to be an ugly number. That's 51.6 recurring degrees for the measure of angle y in this problem. Decimals can happen, ugly decimals can happen. Follow rounding instructions if they're given to you on any assessment. In our second example here, it's the same exact thought process. These are exterior angles. Doesn't matter how many sides the shape has. They have to add up to 360 if they are exterior angles. They got to add up to 360. So a plus 102 plus 73 plus 67 plus 88 has to equal 360 degrees. Only one a, we're combining that 102 with the 73 with the 67 with the 88, and that gives us 330 degrees. And if we subtract that 330 from both sides, we'll get 30 degrees for A, the exterior angle for that problem. In our last scenario, we're finding the exterior angle of a regular 12-gon. Remember again, regular means all the sides are congruent, all the angles are congruent. That also means all the exterior angles are congruent. Since it's a 12-gon, that means there would be 12 exterior angles. So that means the 360 degrees on the outside is just being evenly split to each of the 12 angles. So all we're doing in a problem like this is 360 divided by 12, which will give me 30 degrees for the exterior angle on a regular 12-gon. Great example here at number 15 where we have a square and we're given a few measurements and we need to find everything. It says find all missing measurements, including sides, diagonals, and angles. We're going to start with the angles because no matter how big or small a square is, all the angles are going to be the same in every square. They're always the same. Meaning, from a rectangle, there's 4 right angles. A square has all the properties of a rectangle, so we know all these angles in the corners have to be 90 degrees. From a rhombus, we know the diagonals are perpendicular to each other, and a square has all the properties of a rhombus. So that means here at point O, where the diagonals intersect, if they're perpendicular, they form right angles. So all of those are right angles there in the middle. Also from a rhombus, the diagonals bisect these corners. This corner, this 90 degrees is getting cut in half by the diagonal. If you cut 90 in half, you get 45 degrees on either side, and that happens in every corner, so every 90 is getting cut in half, which means I got 45s on either side of any diagonal in a square, 45 degree angles. This is every square. Every square has these angles, okay? For the diagonals and the sides, we need specific measurements because the square could be big, small, whatever. We're told that AB is 10, Okay, well, in a square, it has all the properties of a rhombus, which is 4 congruent sides. So that means all the sides are 10. This is 10, this is 10, this top side is 10. We're told AO is 7.7. So that's this little piece on this diagonal. And because the square has all the properties of a parallelogram, we know this diagonal gets cut in half. So if this half AO is 7.7, this half OC must also be 7.7. And because the square has all the properties of a rectangle, that means this diagonal DB must be the same length as this one, which means it's also going to be getting cut in half to these exact numbers. So we also have 7.7 for DO and 7.7 for OB. Right. Technically, if we needed all the measurements, we would also add our 7.7s to get the measures of the diagonals here. Not necessary for us to do that in this example, though. That's a square. All the properties of a parallelogram, rectangle, and rhombus. We're in the home stretch here of our study guide work. We're going to be proving shapes on the coordinate plane. If you can understand and grasp how to do this here, then you truly have a good understanding of all of these special quadrilaterals here in Unit 7. We're going to prove that this shape is a parallelogram. Well, a parallelogram, remember, has 4 basic properties. Opposite sides are congruent, opposite sides are parallel by definition. So there's actually 5. Opposite sides are parallel, opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, diagonals bisect each other. Minus the supplementary angles, those other 4 things we can prove on a graph. All right, the easiest one, though, the one I think takes the least amount of time, the least amount of work, is to prove that the diagonals bisect each other. Because if the diagonals cut each other in half, then the point that they meet would have to be the midpoint for both diagonals. So they would have the same midpoint. So that's what we're going to try to prove here in this example, right? We're going to do it one at a time. I'm going to start with diagonal BD. I'm going to be organized and show my work. So I'm going to write BD. I'm going to write down that B is located at 4, 4. That D is located at 8, 1. I'm going to label those points so that I can carefully plug them into the midpoint formula, which is x1 plus x2 divided by 2 for your x coordinate. So that would be 4 plus 8 divided by 2. Then we have a little comma because this gives us a coordinate location. Then we do the same thing with our y's. Y1 plus y2 divided by 2, which would be 4 plus 1 divided by 2. Then we do order of operations. 4 plus 8 up top gives me 12. 4 plus 1 up top gives me 5, so I have to do that numerator stuff first. Now I can divide. 12 divided by 2 gives me 6. 5 over 2 is 2.5. We could write that, or I could leave it as 5 over 2 if I want to. That's my midpoint for that diagonal BD. Again, I can prove this is a parallelogram if AC has the same midpoint. So A is at 0, 1, and again, I'm going to stay organized here. So we're doing AC. A was at 0, 1. C is at 12, 4. Again, I'm going to label and calculate to find the midpoint. So x1 plus x2, that's 0 plus 12 over 2. y1 plus y2, that's 1 plus 4 over 2. 0 plus 12 is 12. 1 plus 4 is 5. 12 divided by 2 is 6. And again, I can leave that 5 over 2 as 5 over 2. Look, I have the same midpoint. So we just need to justify our answer, right? We're being asked to prove that it's a parallelogram. Well, we could say same midpoint, and I'm going to kind of abbreviate some stuff here as we go through. We have the same midpoint, therefore by the diagonals converse, because these diagonals bisect each other, right, this must be a parallelogram. They have the same midpoint, that means the diagonals bisect each other. That means this shape is a parallelogram. In example 17, we have to prove that ABCD here is a rectangle. Okay, what do we know about rectangles? We know that diagonals have to be congruent to each other. Diagonals are congruent in a rectangle. So we just need to prove that in order to say that this shape is indeed a rectangle. So we have a diagonal AC, and we have a diagonal BD. We're going to do those one at a time. We're going to start with AC. We have point A located at positive 4, positive 2. We have point C located at 6, 16. We're going to label those x1, y1, and x2, y2. And the reason we're labeling them is because we can plug them into a formula to figure out how long they are, which is what we need to know that they're congruent. We need to know if they're the same length. And to figure out how long they are, we're going to use the distance formula, right? So if you need to take note of that to help you remember, we have to use the distance formula to determine if segments are congruent on the coordinate plane. So we're plugging these in too. Distance equals the square root of x2 minus x1 squared, that would be 6 minus 4 squared, plus y2 minus y1 squared, that would be 16 minus 2 squared. Then we're doing our algebra. 6 minus 4 gives me 2. 16 minus 2 gives me 14. Then we're doing our exponents. Did those parentheses first there to get the 2 and 14. Now we're doing exponents. 2 squared is 4. 14 squared is 196. And when I add those together, I get the square root of 200. We're doing the same thing now for diagonal BD. Again, I'm going to stay organized. Here's my work for BD. Point B is located at 10, 4. D is located at 0, 14. And I label x1, y1, x2, y2. And I plug into my distance formula. The square root of x2, which is 0, minus x1, which is 10, squared, plus y2 minus y1 squared, 14 minus 4 squared. 0 minus 10 will give me negative 10. 14 minus 4 gives me positive 10. Squaring both of those gives me 100 each. Negative 10 squared is positive 100. 10 squared is positive 100. When I add those together, I get the square root of 200 for both diagonals. So because I have congruent diagonals, this shape must be a rectangle. In 18, we're proving that ABCD is a rhombus. Again, I think the diagonals are the easiest things to work with to prove these. And in a rhombus, the diagonals are perpendicular to each other. We have perpendicular diagonals in a rhombus. Well, how do we figure out if diagonals are perpendicular? Well, we need to know the slope, because perpendicular things will have negative reciprocal slopes. So we're going to find the slope of AC, that diagonal, and the slope of BD, that diagonal there. So I'm going to stay organized. I'm going to start with AC. We got to know the location of our points here. A is located at 2, 2. C is located, where is that located? That's 18, 10 for point C, 18, 10. We're going to label those, and we're labeling because we need to plug them into our slope formula, and we need to do it accurately. We have y2 minus y1 on top. That would be 10 minus 2 over x2 minus x1 on the bottom, 18 minus 2. 10 minus 2 is 8. 18 minus 2 is positive 16. We can reduce that 8 over 16 to 1/2. We're going to do the same thing for the other diagonal. So we're going to do this for BD. Again, I'm going to stay organized. Point B is located at 12, 2. Oops. 12, 2. And point D is located at 8, 10. Again, we're going to label x1, y1, x2, y2, and we're going to plug these guys into our slope formula. So y2 minus y1, 10 minus 2, over x2 minus x1, 8 minus 12. 10 minus 2 is 8. 8 minus 12 is negative 4. 8 divided by negative 4 would give me negative 2, which I'm going to leave as negative 2 over 1 so that we can see that these are negative reciprocals of each other. 1/2 and negative 2 over 1. Those fractions are flipped. One's positive, one is negative. Those are negative reciprocal slopes. Therefore, I have perpendicular diagonals, and therefore, this must be a rhombus. In our last example here, we have to prove, or we have to classify this figure as either a parallelogram, rectangle, rhombus, or square. Okay, we're not giving you the option of any quadrilateral here. It's got to be a special type of parallelogram or just a regular parallelogram, which means that we don't have to do a ton of work. So if it just said classify the quadrilateral, then we'd have to prove specifically it's one of these and it's not any type of other four-sided shape. Right, but giving us just these options, we don't have to do much. Okay, when I look at this, I don't think this is a square or a rectangle because these angles don't look like right angles for me. So visually, I'm giving myself a direction to follow. I'm not saying for sure it's not a rectangle or a square. But I'm giving myself something to look for as I try to prove what shape it is, as I try to classify it. When I think about the parallelogram and rhombus, I need to think of the properties. What makes the rhombus more unique than a parallelogram? Well, there would be 4 congruent sides on the rhombus. And to me, it looks like FG here might be a little bit longer than GH. So I think it doesn't look like a rhombus. Therefore, I have this idea forming that this might be a parallelogram. And I then have to prove that it's a parallelogram. So what things can I show to make it that shape and not the other 3? Well, what eliminates the other 3 options for us, we can again look at the diagonals, and we can eliminate the rectangle by saying that the diagonals are not congruent to each other. Because in a rectangle, diagonals are congruent. So if I prove the diagonals are not congruent, then it's not a rectangle. Okay? Then if it's a rhombus, the diagonals would be perpendicular to each other. So I can disprove that it's a rhombus by showing that the diagonals are not perpendicular to each other. And by showing those things, I also eliminate the square as a possibility, because the square would have both of those. Diagonals would be congruent and perpendicular to each other. So if I can prove the diagonals are not congruent and not perpendicular, then it cannot possibly be those other 3 shapes. It would have to be a parallelogram out of our options here. So that is what we're going to do. How do I prove that they're congruent or not? Well, that is using the distance formula. So I'm going to start with this diagonal, EG. So yeah, EG, I'm going to label them carefully. E is at -1, +5. G is at 4, 4. We got x1, y1, x2, y2. And we're plugging these guys into our distance formula. So x2 minus x1, that's 4 minus -1 squared, plus y2 minus y1, that's 4 minus 5 squared. Doing parentheses first, we get 4 minus -1 gives me +5. We have 4 minus 5 gives me -1. And then we are squaring. 5 squared is 25. -1 squared is +1. 25 plus 1 will give me the square root of 26 for that diagonal. But this is a parallelogram. The other diagonal cannot be this long, right? So let's see. We're going to do for FH now. I'm going to move to the side, try to keep everything on screen here for you. So we got FH now. Point F is located at 2, 8. Point H is located at 1, 1. And we're going to label. And we're going to plug into our distance formula. So distance equals the square root of x2 minus x1, that's 1 minus 2, squared, plus y2 minus y1, that's 1 minus 8, squared. Doing parentheses first, 1 minus 2 gives me -1. 1 minus 8 gives me -7. -1 squared is +1. -7 squared is +49. And when I add those up, I get the square root of 50. So here I have proof. The diagonals are not congruent to each other. So I also need to prove now that the diagonals are not perpendicular to each other. Because saying the diagonals are not congruent just eliminates the rectangle and the square, right? It doesn't eliminate the rhombus as a possibility. Rhombuses do have perpendicular diagonals. We need to make sure that ours are not. How do we do that? We use the slope formula, because perpendicular things will have negative reciprocal slopes. Okay, I'm going to do that right here underneath. I already have those points labeled at the top of the screen. I'm going to use them. Use M for slope, and the slope formula is y2 minus y1. So for EG here, for these points, y2 minus y1 would be 4 minus 5 up top, over x2 minus x1, which would be 4 minus -1 on the bottom. 4 minus 5 is -1. 4 minus -1 is +5. So we have a negative slope of 1/5 for that diagonal. Do the same thing over here with FH, using these points and the slope formula. y2 minus y1 will give me 1 minus 8 on top. And then x2 minus x1 gives me 1 minus 2 on the bottom. 1 minus 8 is -7, 1 minus 2 is -1, and negative divided by a negative is a positive, so we have a positive slope of 7 over 1. Well, 1 is negative, 1 is positive, but we're not flipping our numbers here. 1/5 doesn't become 5 over 1, so these are not negative reciprocal slopes. Therefore, the diagonals are not perpendicular to each other. So, because the diagonals aren't congruent and not perpendicular, the only possible parallelogram this could be is just a regular old parallelogram. Guys, this wraps up our study guide and our review for Unit 7. Don't forget, I forgot to put a mid-segment of a trapezoid example on there, and that will surely be on any quadrilateral assessment that you take. Best of luck with your study, and we'll see you in the next unit, guys. Bye.